students, welcome back. This is Taura's Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please shoot me an email and I'm happy to help in whatever way I can. So lucky you, you get to hear my voice for another lecture. But the best part is we will be learning about hypothesis testing. Yay! So let's go back to the very beginning. One of the first things you learned in statistics is that statistics has a statistical process. It's very much like the scientific process. The first part of the statistical process is starting with a question about the population parameter. We're always asking what's happening with the population, and we're going to use a sample in order to make inferences about that population. During this time, we also start to think about ways that we can reduce error. And looking at ways to reduce error starts with looking at our experimental design. Depending on the question you want to ask will depend on what the best experimental design is for your work. The best type of experiment is one that uses simple random sampling techniques because it reduces bias as we increase randomness. Therefore, we have less error in our final calculations. The next step is gathering data. This is usually the longest phase. This is where we use instruments to take careful measurements. These might be exams, they might be lab tests, they might be medical tests, they might be surveys. Different things like that are used in order to take careful measurements, and we compile all the data together. All the raw data is compiled together. The next step is the descriptive statistics step. During this time, we start to organize the data in tables or spreadsheets, and we start to describe what the physical or qualitative descriptions of the data or the data participants. We also start to look at the quantitative data descriptions. So we're looking at all the measures of center and the measures of variability. At this time, we also do any assumption checking. So checking for normality, or checking for like the central limit theorem, for example, making sure that we meet any conditions that need to be met. The last step is running tests, and these tests are often in the shape of null hypothesis testing, and sometimes these tests are called null hypothesis statistical testing. Using these hypothesis tests, we can make inferences about the population using what is learned from the sample and also using what we know about probability. So what is null hypothesis statistical testing? Null hypothesis testing is a formal approach to deciding whether a statistical relationship in a sample actually reflects the real relationship in the population or if it's just due to random chance. Null hypothesis statistical testing, you often see this abbreviated as NHST. Null hypothesis statistical testing starts with two hypotheses, and they're always about the population parameter. You will have one hypothesis that is called the null, which explains the situation if there were no difference, and there is another one called the alternate hypothesis, which addresses the question. Let's look at this in more detail with an example. Let's think about a deck of cards, just a regular deck of playing cards. How do you know if that deck of playing cards is fair? Well, what are the different pieces of a deck of cards? It has spades, hearts, diamonds, and clubs. And each one of those suits has 13 cards. So for spades, we have an ace, a 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we also have a jack, a queen, and a king. So we have 13 spades. The heart is a different suit, and it also has the same type of cards, so it also has 13 cards. The diamond also has the same 13 cards, and the clubs also has the same type of cards. If we have 13 cards of each suit, then we have 52 cards total in a fair deck of cards. Half of those cards would be black suits because the spades and the clubs are black, and half of those cards would be red suits because the hearts and the diamonds are red. So we can say we have 50% black cards and 50% red cards. even if we weren't looking at the cards and somebody said inside this deck is a fair deck of cards, you would expect this to be the case. 50% red, 50% black. So what if the question is this deck of cards fair according to the proportion of red cards and black cards only? So we're not talking about necessarily the types of cards, but we're just saying if we looked at a fair deck of cards, we would expect 50% red, 50% black. Is this what's happening with this deck? Okay, now at this point you can see the deck, but think of it that all the cards are face down and you do not know what the colors are or what the types are. That's what's happening when you have a population. You don't know what's in the population. They're face down. You can't see it. The population exists and you may never know what the truth is. But if we said, I'm just concerned about the color of the cards, not the suits, not the types, just the color of the cards. If we're just talking about 50% red and 50% black, is this deck fair? Okay. So if the question is this deck of cards fair, quote unquote fair, we would expect that 50% of the cards were red. And if I were going to write this as a proportion, I would write that the probability of drawing a red card is 50%, or the proportion is 50%. If it's not a fair deck, then the proportion of red cards would be not equal to 50%. In this scenario right here, the equal amount of red cards and black cards is the null hypothesis. This is what is expected. And if our question is this deck of cards fair, then we would expect that the proportion is not what is expected, that it's an alternative, and that alternative is the proportion is not 50%. So this one is the null hypothesis, and this one is the alternate hypothesis. This is the null because it's what's expected. This is the alternate because it is what is the alternative of what is expected and what the question is asking. So let's do a little mini experiment here. So here I have 52 cards. Okay. As you can see here, we see that there is a total of 52 cards, and I have drawn one card here. And my question is, if we just thought about the color, 50% red, 50% black, is this a fair deck of cards? Now, none of these cards can be seen. We see here that we have 52. So at this point, it looks fair. And we're going to use simple random sampling techniques in order to see if we get any indication that this is a fair deck of cards. Now, at this point, I have drawn a red card. This is a Queen of Diamonds, okay, red card. And when I drew this, I had all 52 cards down, right? And I drew one, and I got this Queen of Diamonds. And now I'm going to put the card back, right? Mix it up and draw another one. What is the probability of me drawing a red card? It's 50%, right? Because I've got 52 cards. 26 of them should be red. 26 of them should be black. So I have a 50% chance of drawing another red card. So let me see what I get this time. I'm going to go ahead and draw again. Okay, and I get another red card. 6 of diamonds. Okay, I want to know, if I put this card back and I mix them up, what is the probability of me getting a red card? It's still 50%. Okay, this time I got a 7 of diamonds. Great. Okay, makes sense. I'm going to go ahead and put this card back and draw again. What is the probability? 50%. There's no change in the probability. And I go ahead and draw again. This time I get the 10 of hearts. Okay, I'm going to go ahead and put this card in again, mix it up, and draw another card. What is the probability that I will get a red card? 50%. I get another red card. This time I got the King of Hearts. I'm going to go ahead and put it in. Think to yourself, what is the probability of me getting another red card? It's still 50%. It's 50% because there's 50% red cards in a fair deck. There's still 52 cards. So I'm going to go ahead and replace that card so I maintain the same amount of cards in the deck and I do not change the probability, and I draw again and I get a 3 of diamonds. I'll put that card back in. Probability does not change. Still 50% probability, and I'm going to draw another one. I get a red 5 of hearts. Okay? I keep doing this over and over. Every single time, okay, I'm going to keep this total at 52. So you want to watch this 52 and see if this changes. And I'm going to go ahead and draw over and over again. So theoretically, this has never changed, right? There's always a 50% chance of me drawing a red card. But you might start to think to yourself, why hasn't she drawn a black card yet? What's happening? Every single time she draws a sample, she keeps getting red. And I keep clicking on this to show that I'm keep getting red. I keep getting red. I keep getting red. By now, don't you think I would have gotten a black card? Does something seem strange? Well, if you notice here, what did I do? Here it says which suits should be included. I just told it to include hearts and diamonds, and I happened to use 2 decks instead of 1 so that I would trick you into actually thinking it was 1 deck of cards. Okay, now I'm going to go ahead and do things correctly. Draw cards. Look, I got a black 5. Put that card back in, draw again. I got a 4 of hearts. Okay, 50% chance. Let's see. I got a red one, 50% chance. I got a black one. Now, will I always get black, red, black, red, black, red, black, red? Maybe, maybe not. But the fact is that if I did this enough, I would end up getting approximately 50%. If I did an infinite amount of draws, I would get about 50%. And that's what we're banking on, is this probability idea to see, is there enough evidence in a random sample to either confirm that there is no difference between what is expected and what the sample is showing, or that there is evidence that that is not the case. There are 2 hypotheses. The first one is called the null hypothesis. The notation for the null hypothesis is an H with this little 0 kind of a subscript over here on the bottom right corner, okay? And that is pronounced H naught, or the null hypothesis. Then you'll usually see like a colon, and then you'll use the population parameter notation. So here, if I'm working about proportions, I would use a P and then write what I expect the population parameter to be. In the case of the cards, we expected the proportion of red cards in a fair deck to be 50%. So I've written the null hypothesis as H naught, the proportion equals 0.5. Notice that this is an equal sign. All null hypotheses use an equal sign, okay? This is what we expect to happen. So the null hypothesis states if everything is fair, there is no cheating, there are no surprises, there's no change, there's no effect, then this will be equal. If you're using P, we're talking about the population proportion. If you're talking about averages or means, then you would use the Greek letter mu to show that you're talking about the population parameter in terms of beans. It is very important to remember that hypothesis testing is always about the population parameter. It is never about the statistic. because we have gotten to the point in statistics in this class that we are trying to make an inference about the unseen population parameter using our seen or our known statistical sample. The other hypothesis is called the alternative hypothesis. You might see the notation for the alternative hypothesis in two different ways. You might see it as a capital H with a subscript of an A, or you could also see it as a capital H with a subscript of a 1. You'll see the colon, and then you'll have the population parameter notation. If it's a proportion, it's going to be a P, and it's going to be a mu if they're talking about the population means. Okay? The symbol that comes afterwards is going to be either not equal to sign, which is this thing right here, a greater than sign, or a less than sign, depending on what you're testing. And then it will have the same value, the same proportion or the same mean as what was stated in the null hypothesis. The alternative hypothesis is trying to seek evidence to answer your question. Okay, so if your question is the proportion greater than the null, then this symbol would be a greater than sign. If your question is the proportion less than the null, then this sign would be a less than sign. Or if you're looking for any difference, whatever, it doesn't matter if it's less than or greater than, you're just looking for any difference, then you would use the not equal to sign. Again, you have to remember that this hypothesis testing is always in terms of the population parameter. It is not about your sample statistic. Let's look at a really simple example using global warming. So it says, a 2014 Pew poll found that 61% of Americans believed in global warming. A researcher believes that this rate has declined. State the null and alternative hypotheses in words and in symbols. Okay, so right now they're going on that 2014, 61% of Americans believe this. So this is a proportion. It's not an average, it's a proportion. And the researcher wants to see if that number has decreased. So my null hypothesis would be written as H naught colon, the proportion, because it's P in terms of the population parameter. It's not P hat, it's P, equals 0.61. This is the same proportion of Americans that believe the global warming as in the past. So if we did an experiment, we would expect that this would be the same, right? It wouldn't have changed. The alternate is what we're looking to see if it has changed or not. So the alternate hypothesis is P is less than 6.61 because the researcher thinks it's decreased. Not that it's changed or that it's increased. They're looking specifically to see that it has decreased. That's why they're using the less than symbol instead of the not equal to or instead of the greater than. So as you can see, it really depends on the question on how your alternative hypothesis will be stated. Let's look at this situation right here. In this second sort of light green row, we see that we have H naught, H naught, H naught. In this situation, we're saying the proportion is equal to some given proportion. Here again, proportion is equal to some given proportion. And here again, proportion is equal to some given proportion. But let's see what happens with the alternate. Here, we have that the alternate, that P is not equal to some given proportion. It doesn't say that it's less. It doesn't say that it's greater. It's saying that it could be either less or greater because it's different. Because it can be either less or greater, that's considered to be a two-sided hypothesis. In this situation, we're saying that the alternate hypothesis is going to be less than some given proportion. Okay? So in this case, we're only concerned with the proportion in the sample being significantly less than whatever proportion was stated in the null. So we're looking for anything that is quite a bit to the left or less than the null proportion. The opposite is true here. We're looking for something that is significantly greater than the given proportion in the null. We're only concerned with things that are much more off to the right of the given proportion. So while this one's looking for either a greater than or less than change that is significantly different than the given proportion, so you're looking at like two sides of the normal curve, this is just concerned with extremely less values or proportions, relatively speaking, to the null hypothesis that are to the left, and this is just looking for the ones that are to the right. So this is one-sided to the left, and this is one-sided to the right. Let's look at an example using internet sales. Okay, these questions are very similar, so it's really important that you notice where the differences are in the question. So this first question says, during the previous fiscal year, 30% of a retailer's sales were due to online sales. In an effort to increase this percentage, the retailer has purchased ads on social media sites. The retailer gathers data on types of sales during the current fiscal year. Has there been any change in the online sales? Write the null and alternate hypotheses for the retailer. Is this a one-sided or two-sided hypothesis? Okay, well, we always know that there's going to be two hypotheses. So the null is what is expected. If there's no change, then what do we expect from one year to the next? And the alternate is going to answer the question. In this case, what's been happening is that there's 30% of online sales so far with no changes. They've decided to implement the change of buying ads on social media sites, and they want to know if there's any change at all. Okay, so this is going to be a two-sided test, and I'll tell you why. First of all, the H0 is going to be the 30%, right? So the proportion, if nothing changed, there was no treatment whatsoever, we would get the same 30% internet sales from one year to the next. Now, because the researcher, or because this company wants to look to see if there's any change at all, because they use the word any change, we're going to use not equal to, okay, instead of equal to, right? We're looking for any change. What is this saying? It's saying that if there's something that's significantly low, then the proportion that we expect to be right here in the center, or anything that's significantly high, then we're going to go ahead and say that there's a difference. That's enough evidence to state that there's a difference. But if everything is sort of in the center here, that's not enough to say so. So because the person used the word any change, we know it's going to be a two-sided hypothesis. The H0, as always, will have an equal sign, and the HA will have a not equal to sign. The expected proportion stays the same. This is slightly different. Notice what it says this time. During the previous fiscal year, 30% of a retailer's sales were due to online sales. In an effort to increase this percentage, the retailer has purchased ads on a social media site. The retailer gathers data on types of sales during the current fiscal year. Has there been a decrease in online sales? Okay, write the H0 and the HA for the retailer. Is this a one-sided or two-sided hypothesis? So the H0, the null, is going to be what we always expect. The proportion equals 0.3, okay? The alternative this time is going to address the question, have sales decreased? So in this case, they're just looking for values that are significantly lower than the expected proportion. In this case, we're not looking to see if things are higher or there's been any difference. We're just looking to see if things have decreased. So we're just looking for extremely low values. Because low values are in the left side of the normal curve, this would be considered a left one-sided test. Or another way to say this is a left one-tailed test, because it's just working with the left tail. Here's the same question, but there's just one word difference. During the previous fiscal year, 30% of the retailer's sales were due to online sales. In an effort to increase this percentage, the retailer has purchased ads on social media sites. The retailer gathers data on types of sales during the current fiscal year. Has there been an increase in online sales? Write the H0 and the HA for the retailer. Is this a one-sided or two-sided hypothesis? The H0 is the same. It's what's been happening. 30% online sales. The HA is going to address the question, has there been an increase in online sales? Not has there been any change, not is it decreased, has it increased? So, because the proportion stays the same, we always say P equals 0.30. The null hypothesis always has an equal sign, always. The HA is addressing the question, have sales increased? So has the proportion of online sales significantly increased more than 30%? In this case, we're looking to see that if the mean proportion is here, we're looking for things that are significantly greater than the 30%. Things that are greater are on the right side of the normal curve, and they would exist on the far right tail of the normal curve. This would be a right one-sided test or a right one-tailed test because we're looking at extremely high values. There are a couple more things that are really important to mention. First of all, the null and alternate hypotheses must be written down before the data is analyzed. You can't adjust your null and alternate hypotheses to fit your results. That's considered to be very bad form and, as they say, sketchy. Okay? If you change your mind based on what the data is showing, you must collect new data in order to support the adjusted hypotheses. Otherwise, you are introducing bias into your investigation. Again, this is not considered to be at all ethical in terms of data analysis. So what's the big idea? Null hypothesis testing is a formal approach to decide whether a statistical relationship in a sample reflects a real relationship in the population or if it's just due to random chance. The next big idea is that both hypotheses are phrased to answer a question about the population parameter. The null hypothesis describes what is expected if the treatment in question does not affect the sample or ultimately the population. The alternate hypothesis addresses the question of the study and must be stated to reflect if the question aims to answer any change or a directional change, like less than or greater than. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!